what they call internal stability. Okay? And in the internal stability, we talked about the gain of 4. Actually, we should talk about gain of 6. But this week we are going to go through the fundamental limitations one more time. And, so, good work. Good work. Okay, why this is automatically going? Can we do this? Yeah, we are not doing anything, right? So, okay, stay. Well, so we are now in week 5, okay? Week 5. In this week, we are going to focus on MIMO fundamental limitations. MIMO performance, basically we are talking about performance specs as well as limitations. Okay, limitations. Well, I said that control is nothing but an art of trade-off. Control is, so listen carefully. Control is nothing but art of trade-off. What I'm doing here, why do this? Okay. Art of trade-off. So control, you need to answer 2 questions whenever you do. The first question is, what do you want? Okay. What do you want? And the second question is what? What do you know? What do you have? What do you have? Or what do you know? Okay? What do you know? So we need to quantify all these questions. So what do you have? What do you want is basically is kind of like performance specs, okay? Performance specs. And what do you have is the model knowledge, model information, as well as its uncertainties. So that's what we talk about this, okay? Talk about this. And I said this thing many times in different contexts, even in undergraduate course. It's called ME212 Mechatronics. Okay, mechatronics. So we talk about control, right? Control. So if you address this one carefully, then we call this is robust and optimal control. Okay? So exactly the title of our course. So the robust, you need to ask robust with respect to what? Okay? And optimal in terms of what? So you can see the logical flow we are doing in this course. This chapter is to help you to say, what do you want? To tell, okay, what do you want? And what do you know? That's chapter 10, okay? I remember, if my memory is reliable. It's chapter 8 or chapter 10? Oh, no, it's chapter 8, chapter 8. So chapter 8 is to address the second question. So uncertainties. What do you have? What do you know? Okay? So only when you answer these two questions nicely, then we can say we are doing the real control. I said, if you don't learn robust and optimal control, you cannot be what I call a hardcore control expert. Okay? So if you want to be hardcore control expert, you should speak this type of language. Okay? All right. So I hope you see what we are doing today is to answer this type of question. But you may say, oh, what we did in week 1, week 2, week 3, week 4. So in here, we learned week 4, we did what? We did internal stability. It's quite important, internal stability. And we talk about well-posedness. Okay, well-posedness. And we talked about, in the MIMO setting, how we are going to do co-prime fractorization. We can do M of S and N inverse of S. Okay, that kind of a MIMO numerator and denominator. So in the SISO case, you know that in the SISO case, so you have a numerator polynomial divided by denominator polynomial. Okay, so that's a generalization of that. So then, but this one has a different meaning. One is called left co-prime fractorization, CP, co-prime factorization. And then we also have right co-prime factorization. Okay? Factorization. And there are standard steps to do this factorization. In derivations in the future, if we want to develop further robust control in the theoretic side, so sometimes doing this way is more intuitive and straightforward. Okay. So in chapter 3, what we did linear system theory. I call it linear multivariable control. Linear multivariable control. And in this, we talked about mainly linear algebra, linear multivariable control, and we continue to talk about linear multivariable control. And in our chapter 1, 2, 3, and especially chapter 4, we talk about all those spaces we live, okay? Spaces. So, like H2, H infinite spaces, L2, L2, L infinite, okay? L1 or whatever. So, we talk about induced norm and system level, and then we are step by step building up. So now we are here. We are here. Answering this first question. What do you want? Okay? What do you want? But these are considered all the foundations, okay? The foundations. We haven't really talked about robust control versus robust stability analysis yet. So we're going to step by step. Okay, step by step. Move step by step. So I hope everybody understands the whole thing, okay? So let's talk about performance specifications, okay? I have So although you have learned already about the gain phase relationship and the sensitivity integral in terms of a water bed, but those are discussed only in SISO case. Okay, very intuitive. In the SISO case, most of you in classic control, you actually never heard about these two parts. Right, the water bed, okay, sensitivity. Okay. So we need to understand feedback properties. So I showed you that even in the SISO case, so say for example, you should turn this way. So let me do this one more time. So you have reference as your input. This is arrow. This is this. So you have controller. So I'm using a SISO case. Okay. So in studying internal stability, in the end, we know that we should not have a cancellation of unstable poles to the right half plane 0. So then no such cancellation, then it's internally stable. Okay? So that's the ideal case. So you have in and out. So I know that, so here you have disturbance come on in. So this is disturbance in front of this plant. There's another disturbance is up here, okay? This is also disturbance. But sometimes these people say this is L. It's disturbance due to the load, For example, you have a bus, you have a suspension system, depending on how many people in the bus, passengers. So the load is different. So you have one more people in the car, in the bus. So this one is different to bus suspension system, right? But here is like output directly. You have disturbance. That you have sensor. That is noise, and that is for the true value. So we believe this is true value. And true value, you got disturbed, you get Y. So, and this Y is measured. And in the measurement, people also add something like this. Or N. This is kind of a measurement noise. So you can see the system has 1, 2, 3, 4. We have 4 outputs. So the Y is a function of that's like R and DL and D and N. So it's a output due to R. So the output Y due to R, we treat everything else as 0. Then this is nothing but a T. So here the T is defined as closed loop transfer function is CP divided by 1 plus CP. You know this, right? So this is a closed loop transfer function. So then input is like this. Okay? But according to superposition principle, so you add, so if you have DL, you treat everything else as 0, only DL here, okay? Okay? Then what is Y due to DL? So I need to write Y divided by DL is 1. So it's simple. So everything else is 0. So the Y minus Y, so this is a minus Y times C plus DL Okay, then here, then times P is Y, So then what's this? So we're going to have a P divided by 1 plus Cp times dl equals Y, right? So then I call this is T disturbance, okay? So then T disturbance is written as P1 plus Cp. So we don't have this C in here, right? So, okay, so this is like that. So let's talk about this plus what? I don't know. Let's try to derive. So everybody else is 0, 0, 0, 0. So I have y in here. This is minus y, right? Minus y times p times c times p plus d is y. Okay. So then y divided by d is what? 1 plus cp first, then you have 1. Okay. So this is t. What we call this is S. Okay. The sensitivity. S is 1 minus t is 1 plus cp. Okay. So this is sensitivity. So I put this one as S here times d. Okay. Then everybody else is 0, so I have y plus n, then minus, then times c times p equals y again. What I'm going to get is to move 1 plus cp, so you have minus cp divided by 1 plus cp. So this is minus, what is this sum? Okay, so you have minus t. Okay, so I want you to pay attention to this type of thinking. This is called superposition principle. You have 4 inputs, you have LTI system. So you treat what is this one? You treat everybody else is 0. Only focus on output due to, we can say y due to r. We can say this is y due to dl. We can say this is y due to d. We can say this is y due to n. Okay? Make sense? Then you add them together, then you got the total y. Okay? So this is called superposition principle. Okay? So you can see that although this is a SISO case, single input, single output case, we care about it. Okay? But in reality, you have more than 1 inputs. Okay? More than 1 inputs. So usually I want to say, oh, the y should track on my r. So I want to say the system can be actually written in terms of black box. You have r, you have dl, you have d, you have n, right? Okay. But in the output, this is the y. Is considered as we have this y. But in reality, I probably would define something called a z. What is this z? Z is so y is to measure for feedback. But how you can tell the system is good? You probably sometimes you need to pull out this guy as my E, as my output. Because I want to say the E square like bias ITAE, which is, I want 0 to T and P, and if this is dt, so this is called ITAE. So I want to minimize this, okay? Time weighted, okay? Time weighted integral of time absolute zero, okay? Or you can like ISE, like ET squared, the same, okay? So those are, you use this E to make a judgment, okay? So this is kind of like a pull-out signal to treat them as the assessment signal. sometimes you want to make assessment of this signal here. So this is the control signal I add to my plant. I pull out this guy out. So this is considered as my total U. Okay, total U. Add directly to the plant. So then usually I care about this because I want this one to be 0. I want this one to be small. So say for example, I want my UT square, so this is some sort of energy, okay, control effort. But it could be also I have UT dot square T. I want this one to be penalized, so plus. So this is called a smoothness. Smoothness or regularization. Sometimes regularization term. Okay? So of course, if this is 0, I didn't consider the smoothness of my control signal. But in some cases, I don't want my control signal to act too often. It will damage my mechanical parts. Okay? So I add this one as also a penalty. So in other words, so this could be like ddt. So I have u dot t as my assessment signal. So in other words, this c could be a vector of e, ut dot, and so on and so forth. Make sense? So, of course, a lot of cases you only focus on y. Y is good, derivative is good, but in reality, it may not be. So, of course, you can say, oh, z is 1. Fine, you can do that. That returns some previous cases. But from now on, I hope, your performance, when you say, what do you want? What do you want here? What do you want here? You need that variable z. Let's talk about that. What do you want is in terms of the variable z. That z is called performance assessment we pull out for that purpose. Make sense? Of course, in many cases, z is simply y. Okay? Make sense? Yes? So this is more generalized thinking. Okay? I hope. So with that SISO background, and with that, so in this case, you can see we are going to have a 4x4 system. Okay? 4x4. Even if for the SISO system, I can be a 4x4, 4 in and 4 out, right? And then we can have 16. So should we talk about GAN of 16? No, probably not. Well, the reason is you can have a lot of. So it's, oh, what about the U double dot? Okay. All right. So we should not ask. So we should say GAN of 4 is minimum. Is minimum to make sure that everything is internally stable. You don't have a system that looks like stable input output, but internally some variables will go to infinity. You don't want that. Okay? That's last week we emphasized that. Okay, we emphasized that. And today we are going to see this picture. And in this picture, everything is manual. Okay? Everything is manual. So you can see that C is the K is the controller. Okay, is the controller. So we only care about input, output. You have disturbance in front. In front of the plant, you have disturbance after the plant. And you have measurement noise in here, right? And measurement noise in here. So this noise is similar to adding the E, okay? Adding E. So you can see you added the in here, and you got a minus p. And it is the same as r. Okay, same as r. So that's why we don't really talk about this a lot. Instead we are interested in this more. So because you have the same t here, so that's why this scenario is not very interesting. We are interested in this. So, in other words, I think this makes sense. Let me elaborate. Okay, let me elaborate. So, if the system has a true output, the true output you never actually know. Anything you know is already corrupt. So I got a y. No. The y is already corrupt. So this true y is never known. So that's more reasonable. A lot of people don't put d in here, just put a y in here, add noise in here. They are assuming this is already ideal y. And they talk about this ideal y. That's not right. Yes. Of course, they add noise in here. This is correct. This is correct. This signal is correct. But this signal is never know. You never know. You never have that ideal y. This is y star. And you don't have this one, you have this. This is basically a y star. You're talking about y star. Idealized y, you never know. It's not making sense. So if you don't have this one, okay? If you simply write this way, this is already wrong, okay? But what you should really do is say, oh, this is actually my y. So we pull out this one as my y. So when you pull out this one is y, then it's the same as I add this one here. And actually you don't have to care about this because you cannot do it. Now you come back again, okay? It's the same as I add a d, right? So we don't need to care about this. Because this term has similar case like here, right? Okay. Kind of interesting, right? So the reason I call this, so this is called closed loop transfer function. This is called low disturbance transfer function. This is called complementary sensitivity function. Okay? Or we call arrow sensitivity. Transfer function. And the water bed, we talk about the water bed is talking about this guy. Okay, about this guy. So you have something like this, versus you have something like this. So minus plus add together should be 0 if the open loop system is stable. Okay. So this is called error sensitivity from the function has that water bed effect. Okay. All right, let's come back to this. Slide. So I hope you start to remember the sensitivity. Okay, the sensitivity. In our case, the sensitivity has one is called input, one is output. So one is KP, one is PK. So sub I means due to the input. So you put the input in here. So, okay. So you should say, so this is U, this is P. So then, if this is M by N, so then this is M by N. Okay. So these are just two different dimensions. So you should not always assume that your number of inputs. So in here, if I put it here, okay, put it here. So we usually put here this line. Above the line, you write a number. So like this is a wire, but there are so many sub-threads inside. How many wires inside the big wire? So it's that wire here is a vector. So what's the dimension of the vector? M. Okay. What is the dimension of? Okay. Dimension of this one is n. Okay. N. So this is n. Okay. N. So U has to be n by m. Sorry, m by n. Okay. This is n by m. So this is m. This is m. This is m. Okay. So in simulating, in matter of simulating, they do block diagram. They can define that signal is a vector of different size. Okay, different size. So we know that this is you add them to this one. So m by n, this is n by m. Okay. So that's why it's different. Okay, it's different. Okay. So K by P, then this overall system is M by. This is M by M. This is N by N. Okay, M by N. Okay. So these are two different sizes. Okay, but all both square. Okay, square. So the sizes of these two i's are different. This is M by M. This is N by N. Okay, N by N. Okay, and the inverse of that. You look at the Seisel case. They use a sensitivity. So because PK and KP are the same, so then this the same. Okay? But in MIMO case, they will never be the same, even if they are the same size, M equals A. Okay? M equals A. Even if that's true, because in general, KP and PK will not be the same. Okay? Will not be the same. So then we are doing something similar. It's called complementary sensitivity function matrix. Okay, we are adding matrix, transfer function matrix. So this is a transfer function matrix. This is a transfer function matrix. This is a transfer function matrix. This may not be square. So I minus this one, so this is M by M. So then by using this type of simple calculation, it's very interesting. You can pull out the KP, pull out KP. So because it's a 1 minus, you can pull out the KP, you still have it. Do you know why? Do you know why? Yeah, I can derive this one. Can you do a mental math on this? Because this I can be written as this guy times this guy, okay? Then you pull out this guy on this side, so you are going to have I plus KP minus I. Okay, so you have KP left. Okay, so that's why. Make sense? Do you see what I'm saying? Why this is true? I think it's a good idea. We'll do slowly. Okay, we'll do slowly. It's a good idea to check here. Where's my eraser? Now let's do this. So I'm going to show this one to you here. So you have 1 plus I plus KP inverse. I'm going to do I minus this one. This one will suddenly becomes KP I plus KP inverse. So you feel this is a sudden, that is not true. If I write, this is I plus KP, I plus KP inverse. Then you do this one, copy this one minus. So this guy is I. So you have I plus kp inverse. So of course you can pull out I plus kp minus on left side. What's left in here is I plus c kp, this guy left, and minus this guy left, I. So this one will be the same as this guy. Okay? So this type of thing we believe is trivial. But if you feel this is a little bit tough to follow, just I give you an example. I'm not going to explain everything. So this is the same idea. The same idea. You can I minus this guy will become this. And remember, the closed loop transfer function is Cp divided by 1 plus Cp. So it's the same. Cp plus 1 plus Cp. Okay? But there's a difference. One is sub I, one is sub O. Because they have different sizes. And even the sizes are the same, you still need to be careful. Okay? You still need to be careful. Okay? They are different in general. Okay? Different in general. Now, what they do is to apply what? Superposition principle here. Okay? But different thing is everything is vector. So y is a vector. I think this should be small y. Y is a vector. R minus n is also a vector. As I said, this thing is redundant. We can just don't talk about it because it's R minus n. R minus n. Yes, it's R minus n. So you can put n into R, so it's not very interesting. Okay? Then di, okay, di is that guy immediately after the controller k. Then di times dk. So remember, if you write di times t, that would be wrong. Okay, you cannot do that. So this is a vector, this is a matrix. You cannot switch them, okay? Be careful in the MIMO sense. Same is true. Then for what is my u due to p? Sorry, I'm saying, sorry, be careful. So the y due to d, okay, is S0, okay? Y due to di is also S0, but you have p in here. Be careful, you have p in here. Okay. This is y due to input. Okay. So this is TO. This is output sensitivity. But on the other hand, sometimes you want to say what is my control signal, U. So the total control signal U, okay, U, is due to input that K S0. So S0. So it's a K, so you have K. So the control signal. It's also superposition principle. If you pull out the U, pull out this U as an output, yeah, you can pull out the U as output. Then this this output due to input, due to disturbance D, due to disturbance D sub I. Okay, sub I. So you don't have to memorize it, but you really need to have a good sense about symmetry here. So these are all due to output, okay? That's also due to output. So the reason we talk about S sub I, only one place we talk about it. While this, the UP is the total signal in front of the plant, this is the UP. Then it's similar. Similar. Okay. Only difference is this one. There's a I. You need to minus it. Okay. So UP equals U plus DI. Plus DI is 1 minus TI. 1 minus TI is SI. Okay. Because according to this complementary sensitivity function definition. So nothing really strange, okay? Nothing really strange. So you can see that there are two things really important. One thing is called S0, okay, S0. So S0 showed up in here and here, okay? And so what we want here. We want the system output will not respond to the D too much. Better to be 0. Okay? So if S0 is 0, and T0 is 1, but output is input, that would be nice. Okay? And when you have N coupled in here, that's actually, sorry, you cannot do much. It is all called, you heard about it, it's called garbage in, garbage out. The best thing you do is not to increase more garbage, okay? So that's the best thing you can do, because they are coupled. Otherwise, you want to follow your command, then you also follow your noise, okay? So that kind of thing, we should say, we should not consider this N. We should focus on the D. Because basically you are saying your command is not sure, has noise. Then which one I should know, which one to follow. So I think that N is confusing. In many cases, we should not consider N. Just focus on D and DI. Okay? You cannot do much about N. Okay? There isn't anything you can do about N, in fact. And so there's an even worse perturbation. So that's why we say, if you have a bad sensor, take a very bad measurements, and you can achieve something accuracy better than the sensor's accuracy. Are you dreaming? Yes, you are dreaming, because the sensor already bring you the N. You said I can, I paid $10 for the sensor, got a very bad accuracy. But I said, oh, for some magic I can make it, like I spent $10,000 for a very high, precise sensor. That's not possible, you are daydreaming, right? So I'm saying that you couple your noise, this is called sensor noise. It directly contributes to the command following. So in other words, you cannot do better than your sensor. Okay. In other words, the sensor determines how much better you can really do. So for example, my sensor accuracy is 1 millimeter. Then you say, oh, my control accuracy is 1 nanometer. How this is possible? It's anti-physics. Why? It's here. Okay. Of course, this kind of accuracy is frequency dependent, no matter what. Okay? No matter what. You're going to always have that trouble. Okay? So, disturbance rejection at the planned output. Okay? Meaning this is disturbance. I really, really hope this is small, but cannot be small all the way in the frequency domain. So it should be small. Small means less than 1 is small. Small means attenuation, meaning when this is big, modified by this one, it will be small. Okay? So the attenuation is less than 1. Okay? So both of these guys should be small. Meaning far away from 1, so below attenuation. So that's what we want, yes. Naturally we want that. So this is called disturbance rejection in output. Okay, in output. That's due to the D. We also want disturbance rejection in the planned input. So in other words, the SI, SIK, all these things should be small, okay? Due to So this one, look at here. This is one here. So this is the control signal due to this control signal due to this. Then we also say this one. This is the control signal due to DI. You have disturbance in here. I have sensitivity here to influence my control signal U. Okay, so again, these are metrics, transfer function metrics. Okay, it's defined as pk here, S0 is on here. So as I said, sigma bar of a transfer function matrix is a maximum singular value. Maximum singular value. And remember, this is not a number. This is a curve. And it's this sigma bar is a function of frequency. Okay? So, but if you search all the frequency, check the peak point, that point is actually infinity norm. Okay? Of this actually infinity norm. And there is a way to say this is because of the inverse of the matrix, so then the maximum singular value is the minimum singular value of this one, and 1 over this. So the same thing. Okay. And of course, this is SO. This is SO. Okay. But it can be SI times P on this side. Okay. So both of these should be small in lower frequency. We're going to have a picture next one. So we just keep saying that disturbance rejection at the planned input should be small. Should be small. It's S sub I. Okay? Sensor noise rejection and robust stability. We basically need to make this sigma bar small, okay, sigma small. Otherwise, I'm going to amplify my noise. The N is my noise, okay? It's called sensor noise, okay? So the best thing to do is not to amplify the noise. Amplify the noise. So basically, let me do one more time here. U-turn. So I said waterbed of this one, I haven't really talked about. So what is my T should look like? Ideally, my T should be ideally. The best idea is all the way 1. So this is ideal, okay? Ideal. This black line is ideal, all the way 1. Log 1 is 0, so this is okay? All the way 1, that would be nice. But in reality, you cannot. So because of this one, so this is very small. So remember, T is 1 minus S, T. So this is very small, T is very close to 1, okay? So very close to 1, okay? But as S goes to 0, okay? 0. S will go to 1, S will go to 1 as omega goes to infinity, okay? So then T will go to 0. Then when you have T go to 0, then the log will go to infinity, okay? So this is called rolling off, okay? The T, so the T will roll off. Of course, a low-pass filter is something like this, okay? Oh, that would be nice. But in reality, this may not go nicely. It will go something like this. So this is called resonance peak. Our closed loop system, you have something you don't like it, so the noise will get amplified. In noise, in the sensor, this thing here, This is N. We're adding here. Okay. Adding. So this is sensor noise. So we're gonna amplify it directly. So if the whole structure has some resonance, then this peak will make things worse. That's why you heard from the movie, people swing on the bridge. The bridge was, we have many people. The bridge suddenly will have very big sway and crash. You heard about that kind of thing. That's because of this. The amplifier. The unstable. You divide it by 0, basically, at some point. So when you have a resonance peak, so this is called divided by 0, right? Okay. So, well, although these are all the math, my job is to make sure you understand what this is about. But ideally, things will be easier if we do this. So we we know these are what do we want? We want this. Okay, in the minor signal we want this. Okay, we want this. So when we say we want this, then we also basically are saying that we want the PK or KP should be big. That is actually called the loop gain matrix. So this is called, usually it's called L, loop gain matrix. Loop gain matrix. Okay? Okay. So instead of looking at 1 plus PK or 1 plus KP, okay, or KP. So we are going to take a look at this desired loop shape. What, answer the first question, what do you want? We want this shape. So this is omega, so that is, this L is P times K or K times P is loop gain. So this is a low frequency, this is a high frequency, okay? The shaded area are forbidden. Don't touch. So I hope your whole sigma bar, and because L is a matrix, okay? So sigma bar and the sigma under bar are both within this constraint. Say for example, in lower frequencies, you have high gain. In high frequencies, you have low gain. Okay? Then your sensitivity will be exactly like the one we wanted. Say in low frequency, I have attenuation. In high frequency, I have 0 dB. It's not amplifying anybody. Okay? Because this is very, very small, to 0, close to 0. It's very, very big. Okay? Very big. So that is ideal loop shape. Ideal loop shape. If you design a control system, if you check your maximum singular value of loop transfer function matrix, and check the low minimum singular value. So then I told you this maximum singular value is function of omega, so it's a curve like this. Minimum singular value is also something like this. So that's a desired loop shape. If you follow the step to design, or you have a L, you have shape, you design what is your K, so that K is a control transfer function matrix. So that design is called loop shaping design, okay? Loop shaping design. But you can imagine that if you only focus on sigma bar and sigma underbar, that design could be conservative, okay? Because the real design needs more detailed performance specifications. So again, K and P, K and P, okay, K and P. But on the other hand, when they say K and P, I said that because the pull out the signal as a assessment to check the performance, you probably want to add a filter to make emphasize that, oh, I only care about this frequency range or that frequency range. So those are weighting filters. So these are weighting filters. Of course, because the vector, the signal is a vector, then these are transfer function matrix as well, okay, as well. But this is trying to be more general. This is trying to be more general. On the other hand, if you treat everybody here as, if you have a reference here, everybody here is an identity matrix, then this will go back to the same as this picture, right? This picture. Okay, so this one will give you more general type of description of what do you want and what do you have. So of course, when you add in all these filters, you are bringing in more knowledge about the plant signals. So you are also bringing in the second part, what do you know? What about the plant, about the uncertainty? So this picture is already showing those two questions, what do you want and what do you have? Okay. So this is called standard feedback configuration with weights. If you don't have a good idea, just put this weights as I, okay? Identity. Put that. But who knows? Maybe in reality you do know some knowledge about this weighting filters. So this is called weighting filters. You have input signal, disturbance, and arrow. This is E is arrow, and WN is N. Okay, so then what we want is to minimize those arrows. So assuming that you have an input that is an impulse, okay, DI, so DI is here. DI is in something in between here, DI is here. We suppose DI is impulse signal with strengths of eta. Okay, and we assume that the eta transpose expectation is I. So it's a unitary type of impulse. So remember, we are talking about matrix, okay, matrix. So then in the output, I hope the E, of course, is a vector. E square, so this is kind of, I want to make my E small. So basically is integration of the E, okay, and the expectation. And so it ends up checking the so is this clear? You have a WD, S0, and WE. So you should read from left side, right side to left side. WD, S0, WE. So let's see. It's hard to remember. WD S0 WE. Okay, we read WD first. Which one is WD? Is here. WD, then you could times sensitivity, then you times WE. So W is in the end. So E equals what? E equals WE times Y. Y equals D plus this thing. Then you put together, you have loop back. So then you end up with the E due to D, right? E due to D. So that's why you have E due to D. So you have a WD. So here is a WD, okay? U due to this D, tilt. Now we always assume those disturbance are just impulse. Okay, impulse. This one sounds very odd. You need to change your mind. The reason is any signal can be this is something I hope I need to clarify with you. Okay? I need to clarify with you about one thing, okay? So you have a disturbance signal D come over here, add to the system, okay? But if I say D has Laplace transformation of D is capital D of S, okay? The capital D of S. So I clearly can write D is supposed to be generated by D of S with delta T as an input. Make sense? Because Laplace transformation of delta T is 1. Okay? So then the Laplace transformation of output should be ds times Laplace transformation of d. So then it's the same. It's the same. So sometimes you may say this is called a disturbance generator. So how this signal was generated? It is generated by its Laplace transformation, a system with transfer function matrix that is D of S with input is delta. Make sense? So sometimes you may say, oh, the system is system and signal is system. Signal is not a system. System is not a signal. But if you introduce impulse response, the boundary between signal and the system is like this one here. You can say, oh, D of S is a signal, but here is a system. Okay, so I hope I didn't confuse you. So therefore, you can see that why we have from D tiered times WD, okay, times sensitivity, you get here. So Y due to D is the sensitivity, right? So D tiered WD, then sensitivity to Y, then times WE. So that's why E equals WE times sensitivity times WD times D tiered, okay? But the D tiered Laplace transform, sorry, is 1. I don't care, I just don't care, okay? So that's why your arrow is simply right in this way. Can you see? WD, then sensitivity, then arrow weighting, then the 2 norm, then square. It's the same as doing this. Okay? So this is purely time domain signal, norm and expectation and stuff like that. But here is all transfer function matrices. And it's 2 norms squared. Okay. Isn't this beautiful? Yes. Why? Because if you need to compute this one, you need to solve the E. You need to solve the E. You need to solve it. The time domain. You need to solve the system to get this E. And then we do this is without solving anything. We just use transfer function matrix. Make sense? And we're assuming that we can always use all a delta signal in here. So we only care about this weighting function. And so if we say I need a mixture of, I want this, my arrow is small, I also want my control signal small. So you simply add this 2 norm here. So then the performance can be written in the 2 norm square in this way. We have already seen this is the E square. Okay, this is U square times rho, and you put this stack together. The transfer function matrices. So again, you can see this is called weighted or mixture of the performance. So again, if you say, oh, I want U-tiered, the U-tiered dot, the smoothness condition should be there. Yes, we can do it. So these are H2 performance. So we can simply focus all the transfer function matrices. Focus on the 2 norms to solve that without solving the system E of T. Otherwise, you solve the system it's tedious. So then we talk about H infinity performance. It's the same idea, okay? Same idea, H infinity norm of this transfer function matrix. And this is, of course, use 2 norm to induce that and check the maximum peak value. Then this is infinite norm or E infinite norm, okay? Same thing for control signal is same thing here. And if you want to do this, you can write it in this format. So combine the colors. So today we did a very simple thing from SISO superposition principle to the MIMO superposition principle. And we have sensitivity functions. And then we had a more general framework by talking about weighting filters. That will make us in a very general setting talking about how you specify or do the specs, performance specification. So usually it's 2 norm and then H infinite norm. And this one will be in chapter 8, okay? 2 weeks from now, about uncertainties and models. But for the performance specs, we can simply say, oh, we just use this one and minimize it. You choose K to minimize it, so this is called optimal control. You have performance metrics, then you have optimal control. But we haven't talked about robustness yet. Okay? Yeah. But even that, there is a question about, before we really do that, do we already know what's the best achievable parameters of these things? That's called performance limitation. So you know beforehand that what is your fundamental limitations that you can achieve. So that's achievable performance should be known in advance. And this is our next lecture, talking about the minor case body gain phase relationship, the water bed effect, and some other analytic limitations. So, as you can see, the whole lecture, 1 hour, we only went through 6 slides. It's not very slow, it is very packed. So I still suggest you don't miss class, because I try to interpret everything to you to establish your visual concept. On the other hand, you should read textbook. So in the directory of a week, so I gave you this. Every chapter I pull out for you, so you can just read. So there's only 20-some pages for just read it. So I think it's not very hard to follow. So you have already seen all these things. So I'm going to see you Wednesday. We are going to meet Wednesday afternoon 4:30 again for our lab time. I will request access to the room 172. Feel free to stop by. It's good time for lab session, discussion, homework questions, and so on and so forth. So with that, we can stop here. Okay?